Hello YouTube, RJ. Hey, got a big box on the bench today. Got a new instrument for the lab, very excited about. Gonna get her open, take a look at what it is, then I'll explain about it. I'll explain why I decided to get this at this point. This is actually something I'd looked at getting for a while, and we just had something happen that led me to realize I really need to get one of them. And so I went ahead and picked one up on eBay. It's supposed to be in decent shape. We're gonna cross our fingers. Let's tear into it and see what we got. It's an oldie but a goldie. Hopefully this thing is packed up very well. And it looks like they did a good job of packing it up. Got a little thank you card in there. That's nice. And lots of packing. Kudos to that. Let's see if I can get this out. Yeah, they packed it good. All right. Yes, liberal use of bubble pack. I like it. We're getting there. Ta-da! There it is. And what exactly is this? Well, this is a HP 3400A RMS voltmeter. And right off the bat, the first thought you might have is, RJ, why do you need an old RMS voltmeter? Why would you want this? You have more modern meters. You've got meters that can do RMS, but not really. What I'm going to do is I want to go over and jump on the bench a moment and let's talk about RMS. Many of you may know what it is. If I get into it and you do know what it is, you can skip ahead, but I'm going to talk about RMS, but then I'm going to talk about why this is different, why this is a true RMS meter, and why this will come in handy where my other meters won't. You see, if you watch the video where I did the shootout of the shortwave receiver kits, I was measuring the noise floor of them and then looking for the 10 dB signal to noise ratio. And I had to use my oscilloscope to do so. And the signal's bouncing around and I'm kind of looking at it going, it's about this, it's about that. And the reason is I had no meter that I could actually measure that with, because you need an RMS AC meter, but you need an AC RMS voltmeter. You need one that can read up into the frequencies. Most of your handhelds and your bench voltmeters are very limited in frequency. They can be as limited in some cases as hundreds of hertz. Typically they get into like 1, 2, 3 kilohertz, on a really good meter. But when you're looking at noise, you need to be looking at a lot higher frequency than that. That signal's bouncing all over at a much higher frequency. The other thing is those meters are designed to read sine waves, like AC line power, 60 hertz, 50 hertz. They expect sine wave, and they calculate the RMS for that sine wave typically. They don't work for arbitrary waveforms such as noise that are just randomly bouncing around. And so I'm going to jump over and talk about what RMS is, then talk about the differences in that and what noise looks like, explain how this meter does what other meters can't. So join me on the computer for a moment. Okay, let's talk about what RMS is. RMS is root mean square. The RMS of an alternating electric current equals the value of constant direct current that would dissipate the same power in a resistive load. And that means in the same resistive load. So we look here and we see an AC sign, and we look at this area here. If this was a DC voltage with a peak of this, the voltage would go straight up to the peak, come across, and drop straight down. And this would be very easy to know how much energy was in here because it was on the whole time. We only need to measure how long it was and how much there was of it. But when we get into signals, it's a little more difficult because you have some area out here that has no energy. Some of it over here has no energy. So we're left with the peak of the signal. And with a sine wave, it's not too hard to calculate out. You have little chips in your meters and stuff that does this. It expects a perfect sine wave and it calculates out, and it's 0.707 is the average of your peak on a perfect sine wave. For example, in the States where we have a lot of 117, 120 volt at 60 hertz, that's an RMS of the signal. So when we're saying 117 volts, we're talking about right here. That's our RMS. If you measured that to get a peak on a oscilloscope, be careful doing that, make sure you're isolated, you would find about 170 volts up here. So RMS is how much energy is under this wave right here, the red area. The problem comes in when you want to measure something that's not a sine wave, or that is varying, or in many cases is a higher frequency. Your average meter can read, your 60 hertz signal for power. It can read higher than that usually, often up into a few kilohertz. But when you want to look at something like noise, which might be very high frequencies, or signals that are higher frequency, or maybe you're looking at noise in a radio, you want to see what the noise floor is, which would be just ragged spikes here randomly. There's no way your regular meter can calculate how much area is being used and how much power is actually in that area. This is where this meter comes in. This is what it's designed for, higher frequencies plus random waves like noise. It can average even very short little spikes. How does it do this? Well, let's jump over to a little diagram from the manual and the theory of operation, and we'll talk about it. Okay, here's a little flow chart type diagram of how everything works in this meter. And so you have an input, and the first thing you have is some input attenuation and impedance converter. And that's where your range switch scales your input so that we can get a matching output. Once this is handled, where you attenuate properly, fed into what they call a video amplifier with AC feedback. And the output AC comes out and goes through a heating element. Looks like an old tube, doesn't it? And it heats a thermocoupler inside a sealed, insulated little unit. And that thermocoupler is going to produce some voltage, or like a battery, and the voltage it outputs is going to be relative to the heat that it's seeing. Now there's another thermocoupler, and these are all together in a unit. And if you look carefully, you'll notice that the negative of this thermocoupler is tied to the negative of this thermocoupler. There's an important reason for that. Because what we do is once we get a voltage out of this, that voltage runs over to a chopper amp, comes out, and is fed back to the second thermocoupler to heat it, fed through the heating element here. Now this thermocoupler is reversed. They're not in series to produce higher voltage. They're actually differentially connected. So whatever this does offsets this the opposite direction. Now what that does is this. It takes care of a couple issues. One is thermocouplers are not linear, so we could not get a linear output from here. But if we do this, because this one's linearly going to move the opposite direction, we can take the two outputs and do this and get a linear output from them. At the same time, any temperature differentials external to the heating element, both of these thermocouples see, and they're moving the voltage opposite against each other, so it balances those changes out. So it stabilizes it thermally, and it linearizes the output. After the chopper amp, you're thinking, well, okay, but the output doesn't come, it goes to ground here. Well, that's because what you're doing with this one is you're just affecting the voltage we see coming out of here. Sort of like a feedback. This goes back into here, modifies this. This comes back into where it came from, goes in, modifies this, and around and around. But in the meanwhile, we're reading this signal through filters, output amps, and running it through a meter to get a reading. It's a very ingenious little setup, considering they couldn't come up with any other way at the time to calculate these random signals. But if you're looking for how much DC power it would take to heat something equivalent, by literally heating something and measuring it, it doesn't matter what waveform you send in here or at what frequency, you still get a reading of how much energy was put in here. It averages it, it kind of deadens the needle so it doesn't wobble so much with slight variations. So it's a really ingenious way. The guys really pulled off a really smart way of doing this, and it works very, very well. This meter is really fantastic for measuring noise floors for radios, doing signal to noise ratio measurements, those kind of things, and that's why I wanted this meter. So with that, let's jump back over on the bench. And you know how Dave Jones always says, don't turn it on, take it apart? That's what we're going to do. Before we power this thing up, we're going to open up the side, take a look in it, let you see kind of what's inside this thing and what makes it so unique. And then we'll put some power to it. We'll see if this thing works, and we'll try to see if we can measure a signal with it. Give me a second to get out everything, and we'll get at it. All right, I'm already in trouble because I had to break the calibration seal, don't remove seal. I did notice that, if you didn't pick up on it, this was calibrated in 93. It ran out in 10/14/94. So interesting that it was calibrated that, as old as this device is. I believe, I got to look again, I believe this was made in 72. So it's got a little age on it. Doesn't look too bad considering. Doesn't look too bad in there. Pretty clean looking. This is the interesting part. This is the part we talked about. This right here is the thermocouplers, the two thermocouplers, number 1, number 2. We can see it hasn't been, that board hasn't been recapped. Those look like they were the original. Everything looks pretty good in here. Let's carry on. Let's see what we can, go ahead and finish opening it up. Take a good look inside. Get this back one off. All right, there's the top off. What do we see? Okay. Now it looks like the original capacitor is in there for the power supply. Wonder how good they are. Yeah, this board in here is flopping around. I don't know if you can see down in here, but see that board's flopping around. There's foam that's supposed to be in the ends there to hold that, and it's not there anymore. Originally, that was in there to protect a new Vistor, a metal, little tiny tube, tiny little metal tube. But this one is a more modern one that does not have that. It has a JFET in there instead. So it's not going to be as sensitive to vibration, but thinking that's something I'll do is probably take care of that problem. And I've got a feeling I'm going to end up recapping the power supply board back here. Probably because of ripple. I got a feeling if I measure the ripple on this, I'm going to find out there's quite a bit of ripple. Caps cannot, after all these years, be that good. Maybe I'm wrong. Maybe they are. But I doubt it. It's time to turn it on and see what happens. So let me get set up for that. Okay, here we are. I've got the variactor set up. Turn him down. I've got the dim bulb hooked up just in case, just to be on the safe side with this thing. Let's play it safe. So I'm going to go ahead and turn my variactor on. I've got the voltage down to nothing. I'm going to go ahead and turn on this. I'm going to switch on here. And I'm going to bring up the power. And I'm going to turn the light off here, which is going to make the video a little poor, but help me see the dim bulb if it starts to do anything. Meter's starting to act like she wants to work. I don't see any glowing in the bulb. I'm not pulling we're powered. Okay, I'm going to say we can turn her off, take her off the dim bulb, take her off the variactor. Okay, we've got it hooked up. I've got a coax running up to my signal generator. I'm going to use it for testing because I can put out a AC waveform and control the voltage. So let's get this thing on. And of course it takes a minute to warm up. I've got this out in case I need to zero the screen. See what we end up with. Coming down, hopefully she'll get down to 0. Signal generator is putting nothing out at the moment. Looking pretty good there. Signal generator set up for 1 volt RMS, 400 hertz. So let's kick on and see if we read anything. Oh, pegged hard. Let me turn that down. Here, just coming off. I'm half a... Oh, I know what's going on. I'm being dumb. Hold on a minute. Let me turn this off. This thing's not 50 ohm. This is expecting 50 ohm. But I can put this into high Z, and now when I set it to 1 millivolt, that would make sense. It's 500 millivolts was reading about 1 volt because I was on 50 ohm impedance on my signal generator, but this isn't 50 ohm. It's high impedance. So let's try this again. So I've got 1 volt RMS on the signal generator at 400 hertz. Let's see what happens. Hey, that looks better. Now, it's not exact. I wouldn't expect this to be perfectly in calibration after all these years. I noticed the needle's not bouncing. If your filtering in your power supply is shot, you tend to have a waver with these meters. So that's it's nice that it doesn't have that. That's good. That means we can't have much. The ripple rating in this is 1.1 millivolt, so it's pretty tight. And if it gets much above that, the needle starts to waver. And the worse it gets, the more it wavers. And I notice this meter, this thing is sitting pretty rock solid. So I'm going to go ahead, even though I probably should go through and do the whole calibration, and we probably will. We'll go through and probably do a whole calibration on this before we're done. Just to start with, I'm going to go ahead and see if I can zero this 1 volt calibration. Right here on the side, let me turn it around where you can see. Every range has different frequencies and different voltage. This is the 1 volt 400 hertz, and I'm putting 400 hertz out sine wave right now. And so I'm going to go in and try to do an adjustment on this, see if I can, my non-metallic screwdriver here, and see if I can find the pot and get in it. Will she cow is my question. No. Can't quite get her up to 1. So we're probably going to have to do a little work on her to get her. Probably going to have to go through, do a testing procedure, figure out why I can't get her into cal. And it may be if I start with the calibration procedure at the very beginning and move through step by step, things may line up. I'm going to do a little research on that. I think this is probably enough for an introduction to it. So 3400A RMS voltmeter, somewhat working. Doesn't look like it's quite in calibration. Let me do a little research, do a little tweaking around. I'll come back in the next video and show you what headway I've made with this meter. So